All right, hi everybody. This is worksheet 1 on electric force and electric fields. We're going to start by going over the useful formulas and key concepts. So I just want to quickly establish kind of the fundamental, like a cornerstone of this unit here, which is charges of the same sign repel, and then charges of opposite signs attract. So that's something just keep in your back pocket. We should be comfortable with that. We know protons are positively charged, electrons are negatively charged, and they both have the same charge of 1.6 times 10 to the minus 19 coulombs, okay? Moving on to Coulomb's law, that is the magnitude of electrostatic force between 2 point charges, and they're going to be separated by a distance r, and then that r is squared. In this, we have two constants. First is that k constant right here, and then depending on how the equation is being expressed, we'll have an E naught there. I do want to, sorry, I wrote this in my notes here. I do want to note that this applies in point charge form, and kind of I'm going to keep saying this over and over. With forces and fields, you don't plug in the negative. See how they have the absolute value signs here? You don't plug in a negative, but rather you allow the coordinate system and the drawing, the free body diagram, tell you if it's going to be negative. So by that, I mean, oh, I can't draw right now. If you have a standard coordinate system where you have the y-axis pointing north and the x-axis pointing east, if your arrow, your vector itself points east, that is a positive force right there, positive electrostatic force. If it is pointing to the west, so that means it's now disagreeing with what you defined as positive on the coordinate system, you'd plug in a negative, and you're going to see that applied later on. Total electric force is just, the sum of forces relative to a single position. Electric field is infinite around a point charge, right? So it's like this infinite space. It goes on forever, but as r squared gets bigger and bigger, this number itself is going to become so small. So yes, it's infinite, but it has diminishing returns, exponentially diminishing returns, I should say. And this is, again, very important. Highlight this. The electric field points away from a positive charge and towards a negative charge. This is always the case. So whenever you have an electric field vector, the direction the arrow is pointing is away from a positive and towards a negative. So if you have a question that says the electric field is pointing westward again, let's say, you can imagine there's a bunch of like plus charges on the non-arrow side of the arrow. Okay. And you should appreciate the interconnectedness of these two equations here. So you can solve for the electric force, so that being this, when you know the electric field at a certain position, right? So a lot of times they'll say solve for the electric force and the electric field. So depending on what they give you, you can work through them, and you can either plug in the field here to solve for force, or reverse the equation such that, like over here, so you can solve for the field. And did I have something else I wanted to say here?
I have a quick question.
Yeah.
So how the electron, will that be given since it's like always that, like the proton and electron are always that?
This value right here?
Yeah.
I haven't seen your guys's formula sheet, so that could be on it. Oh, that's actually a good point. You reminded me. We need to ask him to upload the formula sheet for the exams kind of as soon as possible, because I want you guys to be very comfortable using that formula sheet. Definitely, you don't want to be the first time seeing the formula sheet on the exam, because you're not going to know where to orient yourself. You're not going to know what is and what's not included. So I guess to be safe for now, I'm going to say try to commit this to memory, but depending on how the formula sheet looks, maybe you won't. I think typically this is given though.
Okay, and we can use that formula sheet during the test, or?
Yeah, so there's going to be one that he provides you, and yeah, so that I haven't seen it yet either, but I'm going to come to class tomorrow, so I'm going to ask him to upload that, because I think that it's important you become comfortable with it. Otherwise, when you first get it, you're going to look for like you're not going to know where things are,
Okay. Yeah.
So there's I leave you guys a little note section here, and there's a few things I want you to add. Actually, it's just 3 points. So very generally, first is charges can flow freely through a conductor. So a conductor is like metal or something. While insulators, that's glass or wood, cannot transfer charge. And if there was even a charge in it, it would remain constant. So the big difference is, charges can transfer freely through a conductor. And if it's in an insulator, there is no transfer of charge. And I'm going to again highlight this point. The electric field points in the direction of what a positive charge would move. Okay, so you can imagine if there's an electric field arrow. I'm going to stop my screen share now and use the video component because I think this is drawing time. So you guys can now all see me on the big Zoom screen, me on video. Can I get like a thumbs up or something?
Yep, we can see you.
Okay, thank you. I appreciate that. And I'm stepping away from my computer. So if you have questions, I think you need to speak up because I might not pay attention to raised hands over there. Okay, so I said electric field points in the direction of where a positive charge would move. So if we're given this vector right here, so electric field, it's going to be pointing in the direction of electric charge would field. So if we drop a little charge in here, let's say it's a plus charge, how will this behave? I'll tell you, it's going to behave such that the plus moves this way. As I said, with an electric field, you can almost imagine like a bunch of little pluses here because it points in the direction a positive charge would move, and minuses over here. So it's going to kind of move that charge that way. I think there was one more thing. Yeah. So again, for your notes, these are the exact words. The electric field points in the direction of what a positive charge would move. And the next thing I would like to say is the electric field at a specific point is created by, I'm going to say, everybody else and acting on you. So by that, I mean, like I remember, these electric fields are like every direction, huge, and go on forever. But if you're asking for it at a specific point, if there's a charge there, it's everybody acting on you, but the charge of that specific thing isn't accounted for. And I think we'll see that through in an example. The words, though, I guess, actually, I regret saying that because that wording was kind of confusing. We'll see it in an example. And this last one should take you back to 135A. And this is a very important point is when you have a negative charge, when you have a negative, when do you plug it in? With vectors, you never plug it in, but with scalars, you would, right? So a vector, the negative is accounted for by the free body diagram, right? So this is kind of what I said earlier. If we have our standard coordinate system, we let the direction of our arrow, let's call this force 1, tell us what the sign of force 1. So in this case, since they agree in direction, we know it's positive. Oh. I'm going to make someone, is anyone comfortable being co-host so you can keep admitting people if they come late? Or
I don't know how to admit, but I can do that.
Okay. You'll get a notification as co-host that like someone's trying to join. I don't know, it's kind of late to join now, but just in case you're co-host. And now if we had a force pointing this way, let's call it F2, it disagrees with our coordinate system. So if we're to do a sum of forces in this scenario, we'll say F net equals F1 minus F2. It doesn't matter what the actual charges that were like here and here, if they were positive or negative, whatever. Remember, we have the absolute values on that Coulomb's law, but rather the sign is determined by the free body diagram in relation to the coordinate system. I know it sounds like I'm harping on that point, but it's just too important to remember. And a vector is a force or a field. So, a force, and this also applies to electric fields. All right, so now with that kind of busy work out of the way, we can start with question number 1 here. So question number 1 says we have 3-point charges. We're given all of their charges, and they're placed in a line. The center point charge is 0.35 meters away from each of the other 2 charges. What is the electric force on the middle charge? So essentially, we have like a straight line here. We have 3 charges, 1, 2, and 3. And we know the distance between them is 0.35 meters and 0.35 meters.
Hi, I'm going to speak for the class and say nobody can probably read the 0.35. I don't know what, I can't read it.
that better?
That's great. Yeah.
Okay, so I'll kind of keep that size in mind there. And we know what the charges are in order from left to right. So we have Q1, and we have Q2, and we have Q3 there. Okay, we can plug in our values. Again, that's equal to 65 microcoulombs. That's going to be equal to 48 microcoulombs. And then this last one over here is minus 95 microcoulombs. I'm going to draw my standard coordinate system now. I don't really need anything in the y because there's nothing in the y. And I'm going to need to realize the effect of the charges on this middle one and the produced force. So let's start with Q1. Q1 is positive. Q1 is positive. Q2 is positive. Two like charges will repel each other. So the force of Q1 on Q2 is being repelled that way. Now we can look at the effect of Q3 on Q2. We can see that Q3 is negative. This is positive. That means Q2 is being attracted. So the vector again will point in the same direction. So I'm going to say F1 plus F3. So that basically means the electric force by 1 and the electric force by 2. Okay. So using this setup in my coordinate system, I've established the signs of everything. We know they're both in agreement in direction with what I defined as positive on my coordinate system. Therefore, I can now solve for the force on 2, which is going to be equal to F1 plus F3. I can now expand these using coulombs. So the effect of 1 on 2, so I'm going to say Q1, Q2 over R squared, and then plus K, the effect of 3 on 2. So Q3, Q2 over R squared. All right. At this point, and this is something I recommend you do in general in this class, is you factor things out where possible, and that'll just save you a little bit of time when you're solving these equations. I'm going to get on my knee here to right here. So K, Q2 over R squared can be factored out from both of these, and that leaves Q1 plus Q3. Okay? At this point, all you have to do is plug in everything. So this is a known constant, R squared is given, and all the charges are given. You're going to do all that plugging in, and what's going to come out is 564.24 newtons. Okay. So that's number one. The only other thing I would like to highlight here is the only other thing I want to highlight here is for Q3, do you plug in the negative even though the sign here is negative? No, you don't. You have to remember there's an absolute value on this. We let the signs come from our vectors in our coordinate system. So do not plug in the negative for this guy. Remember, the equation itself has absolute values. So we're going to get the signs from the direction of the vector. Okay, any questions on number one? All right, let's keep it going. All right, so moving on to question number 2 here. So here we're asked to calculate the magnitude and the direction of the net force and electric field on particle C due to the other two charges. So we have a little triangle here. I'm going to draw it real quick. A little triangle like this. This is like wobbly or something. Anyway, and I'm going to draw my coordinate system. Okay, coordinate system. And on each corner we have QA up here. And QA is, it's going to be small. It's going to get bigger. QA is equal to 17 microcoulombs. Here we have QB QB is equal to minus 17 microcoulombs. And here we have QC, which is equal to 17 microcoulombs. Okay. We're also given the lengths of each side, which I'm just going to quickly convert to meters. So 0.15 meters. And all the sides are the same. So I was discussing this earlier, but this is an equilateral triangle. And by definition of an equilateral triangle, each of the angle sides is 60 degrees. So right off the bat, we know, they're all 60 degrees. Okay? So they're all like that. All right, little angle sign. They're all the same. Okay. The next thing we need to work out is the role of these charges on Q3. So let's start with QA. So QA is a positive, QC is a positive, like forces, like charges, the force is going to, there's going to be some repulsion force. So that means the force is going to point straight downwards, and I'm going to call that force, force A. So that's the force of A on C. And then we have QB. The role of QB on QC is a minus and a plus. Therefore, it's going to be an attractive force. So I'm going to have a vector pointing directly towards that QB position. But we remember from 135A, as we recall from 135A, this by itself can't be solved. We need to break it into its components. So that's exactly what we're going to do. We're going to have a horizontal component. I'm going to draw a dashed line. Sorry, it's going to intersect with the 17. We have a dashed line going horizontal and a vertical line right there. So now we have two components. And I'm going to ask, what's this angle right here? Does anybody have an idea? You should know that one right away.
30?
Yeah, that's correct. 30 degrees. So I'm going to call that alpha, and alpha is equal to 30 degrees. So this was an example of a question where you're going to need to be comfortable with your trig to quickly work this out. Or if you were uncomfortable with it, the reality is you could plug, you can use sine, cosine, and tangent to figure out the angles. But, and then eventually get that alpha. But, knowing the little trig will speed things up there. Okay, so at this point, we now have enough to solve for the electric force. And how I knew to solve for electric force first is we were given all the charges. Okay, so let's start in. I'll use this. All right, so let's start in the x direction. So we're going to say F net C equals F net CX plus F net CY. Okay, so that's kind of a quick setup of PyFag there. So the first thing we need to do is find the, well, you can start with the X or the Y, but to me, the X looks a little bit easier because there's only one vector in the X direction. So F net CX is going to be equal to, I'm going to call this FB, is equal to FB. And then what's the trig, I don't know, function that goes after it? So we're looking at the horizontal component relative to alpha. So it'll be FB cosine alpha. Okay. At this point, you're going to need to expand this using coulombs. So that's going to be that K constant. It's going to be my charge, which is QB. Oh, I'm sorry. Oh, yeah, no, I'm sorry. Yeah, I'm sorry. QB and then QC. So my charge acting on your charge, that's my charge acting on your charge over, oh, I kind of freaked out there. I thought I messed up, but it's correct like this. Cosine alpha. And at this point, you should have enough to plug everything in, and you can just solve it out, and you will get 100.11 newtons. Okay. So in part 2 of this is we're going to need to find F net CY. F net CY. Okay. So everything in the Y direction is we first have a vertical component of FB. So FB sine alpha. And then we have FA pointing downwards. So it is pointing opposite to what we defined as positive on our coordinate system. So minus FA. All right. And then similarly to how we just did before, we're going to expand each one of these out with Coulomb. So that's K, Q, my charge, which is B, and your charge, which is C, over R squared sine alpha minus K, my charge, which is QA, and then acting on QC over R squared. All right. And if you have a good eye, you'll see that what you can factor out here is pretty significant because it's a K Q squared over R squared times sine alpha minus 1. So that's kind of a, I'll save you a lot of time plugging into your calculator if you were able to detect that. Okay, so that, and your answer over here comes out to be minus 57.8 newtons. All right, so now we have found our X and Y components. What's left to do here is pull out that F net C. So F net C is going to be equal to the square root of F net XC squared plus F net YC squared. And you're going to plug everything in, work everything out, and you're going to come out with a magnitude. So F net C equals 115.5 newtons. All right, but we're not done yet because forces and fields have directions. And this is a force here. So we need to find the direction. So we know that F net X, that's this guy right here, is positive. Therefore, it agrees with our coordinate system, which just for reference was like this. So the vector of X, F net C X is like this. F net C X. And then Y is negative. So that means it's going to be pointing downwards. So F net C Y. Therefore, F net C itself is going to be some amount below the horizontal. I'm going to call this, I don't know, 5. Okay. So now we need to find that angle. All we have to do is use trig, and we're going to use our tan function. So tan, and that's going to be, the opposite. So F net CY over the adjacent, which is F net CX. This angle comes out to be 30 degrees. You can't leave it like this, so you'll have to say 30 degrees below the plus X axis. All right, and that's part 1, I'll say. We have now found the force and its direction. This moves us into part 2, where we need to find, I'm blocking, where we need to find the field. Right?
I have a quick question before we go to part 2. Could you go over how we went? Okay, so on the leftmost side, right where you are right now, when we had the K, and I think it's like the QB, or not Q, but you know what I'm talking about, the C. And then all of a sudden we have K Q squared with the sine angle minus 1. How did we get from the one on top of that to that formula?
Yeah, great question. So I did a lot of factoring out.
Okay.
And I combined in my Q values. In this case, our charges were all equal to 17. Absolute value around that. So I was able to factor out a Q squared.
Okay. So if they weren't all equal, then we would have just had to do like the messy multiplication. But because we knew that QB essentially is the same as QC, so it's all just Q.
Yes,
Okay,
precisely. Yes, yes.
makes sense. Thank you.
Yeah, and then you're right. It's totally messy multiplication because each one of these is some number times 10 to the minus 6 multiplied by the same thing times this constant over an r squared. It can get messy, so try to factor where possible. Anyway, so we've now we finished that part 1. We found the force and its direction. Let me open up my thing so I can see what part 2 was. Oh yeah, we need to find the field now. So I gave you a particular equation to use when you know the electric force to find the electric field. Okay, and that equation is, I'm just going to write it real quick right here because it's going to be very short, is E equals F, I'm going to call it F net C divided by QC. So when either the field or force is known, you can quickly extrapolate the other given it's a charge that's provided. So we know QC that's given, and we just solve for F net C. So now we can solve for the electric field. So the electric field equals, you just plug in what we solved for over here, and that comes out to be equal to 6.8 times 10 to the 6 newtons per coulomb. Okay, I mean, those units make sense, right? You have a force, which is the unit of newtons, over a charge, which is observed in coulombs. I know to arrange the equation this way, because like I just said, we just solve for force. If it was the other way around, we all need to use field and the charge to solve for force. So kind of get dealer's choice there. All right, I'm going to pause the recording as I erase the boards, and I'll kind of open it up to questions because people like that. All right, we're back. So now we're going to continue with question number 3. So here we have a point charge of 180 millicoulombs, and it's located 40 centimeters to the left of a minus 20 millicoulomb point charge. Where is the electric field equal to 0? So this is something that we actually went over in class. He did an example similar to this. I think he posted the recording. So that'd be a good resource in addition to how we're going to discuss it now. I think we're going to first start off by drawing our picture. So we're going to have a straight line, maybe not so straight line. Sorry about that, bad at drawing. And we know that we have Q1 here, which is equal to 180 millicoulombs. And here we have Q2, which is equal to minus 20 millicoulombs. Okay. And oh, it's located 40 centimeters to the left. So here is 0.4 meters. All right. So what we're asked to solve for is where on this line, and it's going to be on this line because we know they're both on they're all on the horizontal plane here. The electric force, I'm sorry, the electric field is equal to 0. So there's 3 areas it could hypothetically exist. I'm going to call this star 1, star 2, and star 3. Okay. Now I'm going to raise this question to the Zoom. And if anybody answers this, huge high five coming your way. Does anybody have an idea of where it couldn't be? Just right off the bat, right now, we should know one to cross off. Anybody know? All right. So if you remember, the electric field will always point and behave as a positive charge would. So the effect of Q1 and Q2 on any of these stars is going to indicate that. So I'm going to start with the one that we know for sure is an immediate out. That's this one right here. Q1 on this position has the electric field vector pointing to the right. I'm going to write a coordinate system. Simple coordinate system. And then the effect of Q2 on this position, it's a negative. So it'll be again pointing in the same direction. There is no way these 2 charges can cancel out because we get our sign from our coordinate system. These 2 are adding 2 vectors adding on each other. So if anything, it's more to the right. So it's impossible to have them cancel out and equal 0. And per that logic, we know that asterisk 2 position is not correct. So the next one takes a little bit of practice, and this is kind of comes with an established intuition. We're now left with positions 1 and position.
Can you hear me?
Yeah, sorry.
Oh, okay. I just had a quick question. Are we assuming that the test charge is negative if it's attracted to the negative or is positive?
Yeah, the test chart, you assume the test charge is positive. Yeah.
Okay, thank you.
Where is that? Okay, so yeah, the next part kind of comes with a little bit of intuition. You're stuck between 1 and the 3 position. However, what tells you it's going to end up being Q3, spoiler alert, is the magnitudes of both of these values. Per the fact that Q1 is so much greater than Q2, we know it's going to need to be on this side. And we know it's going to need to be on this side. Per the logic, we're basically going to need a way to cancel out this big value. And remember, in this equation, we're over an r squared. Anything over a squared value gets exponentially smaller just by the smallest distance it moves away. So we need that distance to cancel out the strong repulsive force by 180. But just to illustrate why you kind of get stuck between the two, I'm going to draw this. The effect of Q1 on this position is a vector pointing that way. I'm going to call that E1. And then by E2, it's going to be an attractive one. So it's going to be pointing this way. So they do point opposite directions. Similarly over here, it's going to be pointing, E2 is going to be pointing towards, and E1 is going to be pointing away. And then between these two, the judgment call comes per the magnitude of this. Again, Q1 is so much bigger than Q2. We know it's going to have to be the side which is further away from Q1, whichever will get this r squared value bigger, whichever side is the one we're going to need to work with. Okay, so now we've figured out on which side it's going to be. And we don't really know how far it's going to be, so I'm just going to call it some distance x. At this point, we can set up our equations. So by nature of the problem, we're going to want to set up the equation such that E net equals 0. So as shown by our vectors in our coordinate system, we have E net is equal to E1 minus E2. E1 minus E2. We want to show when it's equal to 0, so we're going to bring E2 to the other side, get E1. All right, now we have a set of an equation we can work with. We now need to plug in our charges. So I'm going to call that, okay. Yeah, let's do it this way. So Q2 over x squared, because from Q2 to this position where it equals 0 is x. And we can set that equal to KQ1 over 0.4 plus x squared. And it's 0.4 plus x because we know it's this distance of 0.4 meters plus this distance of x. So now we have enough to solve and isolate that x. It'll just require a little bit of working around. So I'll just show you the algebra here. So we're going to square root both sides. Okay, I'm going to cancel out these k's. So we're left with, to continue up here, is Q2, that's being square rooted, over x is equal to the square root of, what was it? Oh yeah, Q1 over 0.4 plus x. All right, and now you just got to rearrange it such that you have the x's on both sides and plug in everything, and you'll solve for x, which is going to be equal to 0.2 meters. All right. So the main takeaway here is remember that someone in the Zoom said that, yeah, with the test charge, it's positive. And based on the fact that Q1 is so much bigger than Q2, we need to find a way to bump up that denominator such that it becomes smaller so that it'll be able to equal 0 in respect to the net electric field. All right, so that question 3. Any questions on that? All right. Let's move on to 4. Oh, also, I said this in my in-person session, but I missed it in my just now. Question 2 is a type of question that I'd say is common on exams, and then same with question 4 here. So let's do question 4 now. I'll write it over here. So here we have, this whole system. We have a point charge, but we're given a mass. It's at the end of an insulating cord, so that means there's no transfer of charge, it's just dangling there, and it's at equilibrium. And there's an electric field provided when the pendulum's position is 12 centimeters above the lowest vertical position, the field points to the right. And you have a diagram of basically all of that right there. So let's draw our picture. Right, we have like a little rope here, and there's a charge on the end of it. We know the length of the string is given as 0.55 meters. Okay. We know that it's 12 centimeters off the ground. Convert that to meters too. Just going to draw a faint line here because I like to work with my triangles. I'm going to draw a coordinate system. Actually, I'll draw the coordinate system later, and there's a reason I'm going to draw it later. And we have an electric field pointing this way. And remember, our electric field always points in the direction a positive would move. So you can imagine there's like somewhere infinitely far away, there's some plus charges over here. Like there's an electric field's coming from something and it's pointing in the direction a plus. Actually, I'm not going to pointing in the direction a plus would behave. Okay, we have our electric field, and now we can draw our forces. So we're given a mass. We know that means there's a gravitational force. Gravitational force always points straight down. So there's our gravitational force. We know that since there's an electric field acting on this object, who's, are we giving them? Sorry, one second, I have to closely. Okay, so we know an electric field is acting on this object who's at equilibrium. So that actually answers part of this question, which is, what is the sign of the charge? It's positive. It's positive because it is at equilibrium. Had it been negative, the charge would be attracted towards the pluses on this side, right? So because of the fact that the field and the force are in the same direction, and at equilibrium, we know it's positive. So I'm going to say that's the F electric. So I'm going to say Fe. And again, that's because it's positive and it's pointing in the same direction a positive would relative to that position. Okay, there's one more force, and that's because we're on a string. So we have a tension, T. Now, I want to break up the tension into its coordinate system. So a vector like this and like this. Okay, you can call that Ty and Tx. Okay, and I'm going to draw a my coordinate system just a little bit different than you might expect. And the reason why I'm going to do that is going to make sense a little bit later. But the reality is, if you did it the standard way, you would end up getting the same thing. You just have to flip the sign at the end. Okay. So the first thing we need to do is figure out some angles in here. We know this is a right angle, but we need to find what this angle right here is. I'm going to call again that alpha. So here we can use alternate interior angles. So that being this guy right here, which is also alpha. So how do we solve this? We need at least two sides. We don't know how far this is. And as of now, we don't know what this is, but we do know what the hypotenuse is. We also know that before it's at equilibrium, so you have like a string like this, when it's flat like this, it is exactly 0.55 meters off the ground. Therefore, this height in this iteration, as it's now 0.12 meters off the ground, is equal to 0.55 minus 0.12, which equals 0.43. So we know what this side is, 0.43 meters. At this point, we have two sides. We can now use that and a cosine function here to get 0.43 over 0.55 to solve for alpha. And alpha is equal to 38.6 degrees. So we also know by this logic that Ty is going to be equal to T cosine alpha, and Tx is going to be equal to T sine alpha. And just a refresher, how I know when to use sine or cosine. If the component is touching the angle of interest, it's always cosine. If it's opposite to the angle of interest, it's always sine. Okay. So at this point, we now have enough to work out this problem once we have space. All right. So now we can work out the rest of this problem. What we need to do is start with E. So the sum of the forces in the y direction. And you guys have seen, I've now kind of used different notation to cover like the different ways people learn it. So you can write E net y, the sum of forces in the y direction. That's what that symbol means. Whatever you're comfortable with, they mean the same things. I don't know, I just kind of mixed it up. So in the y direction, we have that tension pointing in the same direction of our y component. So T cosine alpha, and we have the gravitational force pointing down, so minus mg. Okay. We know the forces in the y direction are equal to 0. And the reason why we know that is because it's at equilibrium. It's not like shooting straight up or falling down. It's at equilibrium, so it's equal to 0. So we're gonna, set it equal. I'm not gonna have enough room to keep that here, but remember it's equal to 0. So I'm gonna rearrange it. So T cosine alpha equals mg. All I did was bring the mg to the other side. And now we can solve for tension, where T equals mg over cosine alpha. Okay. And now I'll reveal the reason why I have my coordinate system pointing this way, where a standard one would point towards the east. And that's because I knew that when at equilibrium, the sum of forces in the x direction and y direction are equal to 0. And I'd prefer to work with a positive sign. So by having it come out minus relative to my coordinate system, I know that I'll be able to bring it to the other side and make it positive. And I'll show you what I mean. So the sum of forces in the x direction equals T sine theta, and that sine theta, x component of tension agrees with our coordinate system, and it disagrees with our electric force there. So it's going to be minus Fe. We know it's equal to 0 again, so we can bring Fe to the side, and it becomes a positive. Very nice to work with. And T sine theta. Okay. And now we have to ask yourself, what are we solving for here? That's being the magnitude of the charge. So the magnitude of the charge is embedded in this variable. So we need to open up the equation. So what is F electric equal to? It's equal to the magnetic field times that charge of interest. So now we can solve for Q, which equals T sine, I wrote theta here, but it's alpha over E. Okay, and E was given. So at this point, you can solve for Q, which is equal to 8.23 times 10 to the minus 7 coulombs. And we discussed it's a plus charge. And again, it's a plus charge. I'm going to go back and read the words verbatim that I told you. Here we are. All right, we know it's a plus charge because, and again, I quote here, the electric field points in the direction of what a positive charge would move. So I know a positive charge is behaving this way. This charge is at equilibrium. So that means the force is holding it up from its normal position, which would be down here. Had it been negative, it would have swung the other way and get attracted towards it. but here it's at equilibrium. So that means there's enough force that keeps it positive and holding it up. So if you were to move my phone being like the beginning of the electric field, if you would move it closer, it would cause it to go up even more, right? So that's how we know it's plus. The only other thing I want to add is this equation EQ, which is, FE equals EQ. We use that when the electric field is known. And then you'll use, and I already said when you use the other way, which is when the force is known. Okay? And when the force is known, then you can find electric field if you know the charge. I'm going to sum it up there. That's our last question on this worksheet. I think this last one's also really good practice of kind of an exam-like question because it incorporates field and force. And you also have to remember your forces on the free body diagram. Tomorrow, this is just for the people watching the recording. On Thursday, we're doing a homework Q&A from 6 to 7. So email me questions if you have any, and we'll go over it then. Other than that, I'm going to stop the recording and take any questions from the students on Zoom. Thanks for watching.